You know, in some of the simplest models in physics, you can find these hidden symmetries that are so perfect, they honestly feel like magic. Today, we're going to go on a little journey that involves flipping spins, reversing time, and uncovering this beautiful, invisible balance right at the heart of how magnets work. So, our story kicks off with something called the Ising model. Just think of it as taking the super complex reality of magnetism and boiling it down to its absolute essence. We've got this grid of tiny little magnetic moments, we call them spins, and each one has only two choices. It can point up or it can point down. That's it. It's physics in its most beautifully simple binary form. Now, in this simplified little world, we immediately find a very basic and honestly pretty intuitive kind of balance. Physicists call it Z2 symmetry, which is just a fancy way of describing a system that has two equal and opposite states. Let's see what that actually looks like. Okay, imagine a parallel universe where every single up spin in our system is suddenly a down spin, and every down is now an up. Here's the kicker. As long as there's no external magnetic field bossing them around, the energy of the system stays exactly the same. The fundamental rules of the game just don't change at all. All right, before we go any further, we need to pick up a crucial mathematical tool. It looks really simple on the surface, but trust me, it's the key that's going to unlock this entire idea. So here's the big question. We're not just looking at one particular arrangement of spins, like up, down, up. No, we're thinking bigger. We're considering the total sum of some property, we can just call it F, over every single possible configuration that the system could ever be in, all of them. And here is the rule. It's a really powerful mathematical shortcut. It says that the sum of some property over all possible spin states is exactly equal to the sum of that same property over all the flipped states. Now, we're not flipping the value of the property itself, just the spin configuration we're looking at. It's a subtle point, but it's absolutely crucial. Think of it like adding numbers. If you sum 0 plus 1 plus 2 plus 3, you get 6, right? Well, if you sum 3 plus 2 plus 1 plus 0, you also get 6. The items you're adding are in a different order, but because you're summing over the complete set, the final total is identical. This is a really powerful concept. So we've got this perfectly balanced world. Now, let's break it. Let's introduce a disruption. What happens when we suddenly turn on an external magnetic field? So just to recap where we are, without that external field, our beautiful up-down symmetry is perfect. Our universe and its flip-spin twin are totally indistinguishable. But the moment we introduce an external field, we'll call it H, it picks a preferred direction. All of a sudden, up is not the same as down. The spins feel a pull. They want to align with that field. And just like that, our simple symmetry is broken. So the symmetry is gone. Or is it? To find it again, we have to look for a much deeper, much more profound kind of symmetry, one that's connected to the very arrow of time itself. It turns out there is a way to restore the balance. If we flip every single spin in the system, the laws of physics will only stay the same if we also flip the direction of the external magnetic field, from H to minus H. The two things have to happen together to keep the physics invariant. And this shows you exactly why. It's a perfect chain of logic. See, a magnetic field is created by moving charges, by an electric current. So if you reverse time, you reverse a particle's velocity. Reversing its velocity reverses the direction of the electric current. And if you reverse the current, you have to reverse the magnetic field it generates. It all connects perfectly. Okay, now for the grand finale, let's see how all these pieces click together to show us this stunning, hidden balance in the laws of thermodynamics. So here's the big takeaway. While the system isn't symmetric under a simple spin flip anymore, it is symmetric if you flip the spins and flip the magnetic field. This means the total thermodynamic behavior of the system, the big picture stuff, is exactly the same whether the field points north or south. This profound relationship is captured beautifully by this simple little equation. Z here is what's called the partition function. You can think of it as a master number that once you calculate it, tells you everything you need to know about the system's thermodynamics, its energy, its entropy, the whole shebang. And this equation tells us that this master number is identical whether the field is H or minus H. But hold on, this should make you pause for a second. How is this even possible? We know for a fact that the energy of any single state is completely different, right? For example, a system with all its spins pointing up has a very low energy and a strong up field. but a crazy high energy and a strong down field. So how can the totals possibly be the same? And here is the absolutely elegant solution. In the system with field H, the all spins up state is the low energy, most likely state. But in the system with field minus H, that same all spins up state is now super high energy. The low energy state in that system is now all spins down, which is the exact flipped version of the first system's favorite state. And this is where that summing rule from the beginning makes its grand return. See, the partition function isn't about one state. It's the sum over all of them. The set of all possible energies in one system becomes a perfect mirror image of the set of energies in the other. So when you sum them all up, the totals are exactly, mathematically, identical. It's perfect. So what does this all mean in the real world? Well, it means the partition function is the same. It means the Helmholtz free energy is the same. It means that all the big, macroscopic, measurable thermodynamic properties you could possibly think of are completely indifferent to whether the magnetic field is pointing up or down. It's just a beautiful example of a deep symmetry hiding just beneath the surface of something we thought was simple. And it really leaves us with a final question to chew on. What other elegant, invisible rules like this are out there quietly shaping the reality we experience every single day?